Hey everyone, ready to dive into something powerful?
Powerful, literally.
Yeah. Okay, so today we're looking at alternating current, Chapter 7 from your Class 12 Physics textbook,
A big one.
for sure. Big thanks to the National Council of Educational Research and Training, that's NCERT, for making this chapter available.
Absolutely. It's a fundamental chapter for understanding electricity in our modern world.
I mean, think about it. AC is what powers most of our devices, our homes.
Yeah.
It's the backbone of the entire power grid.
And what's fascinating is how AC is different from, let's say, direct current or DC.
Right, DC flows in one direction, constant, like a steady stream.
Exactly. But AC, it changes direction periodically, like a wave. It's constantly going up and down.
Like a sine wave, right?
Exactly. And the chapter focuses specifically on this sinusoidally varying AC, which is the most common type.
So the electricity in our homes, that's AC.
It is constantly switching direction many times per second.
Whoa, okay. So if it keeps changing direction, how do we even measure it? How do we use it consistently?
That's where RMS values come in, root mean square.
RMS values, okay.
These are like the effective values for AC voltage and current, the values we use to calculate and make sense of it all.
I see, so it gives us a way to work with AC in a more practical way.
Exactly. For example, when we say the electricity in our homes is 220 volts,
Yeah.
that's actually the RMS value. The peak voltage, the highest point of that wave, is much higher,
Much higher. How high are we talking?
around 311 volts.
Wow, okay.
And that's one reason why an AC shock can be more dangerous than a DC shock at the same voltage. Something to be careful of.
Yeah, for sure. Makes sense why this is all so important to understand. Now, I remember finding the whole concept of phase differences a bit tricky.
Right, so think of it like a race
Oh, right.
between voltage and current in an AC circuit. Sometimes they start together, peak together, no phase difference.
Okay.
But other times, one might start a bit late.
So they're out of sync.
Exactly, and that's what phase difference tells us, how much they're out of sync.
Okay, now it's starting to click.
And to help visualize this, the chapter uses phasors. They're like arrows, rotating like hands on a clock.
Okay, I'm picturing it.
The length of the arrow represents the amplitude of the AC quantitor, and its rotation shows us how that value is changing over time.
Got it. So it's a visual representation of the AC quantity.
Exactly. And by looking at how different phasors relate, we understand the phase differences between them.
Makes sense. Yeah, things start to get really interesting when we bring in inductors and capacitors.
They're like the rebels of the AC circuit.
Uh-huh. Right. Always
Yeah.
causing those phase differences.
Exactly. So let's start with inductors. Imagine it like a coil of wire, but stubborn.
Stubborn. How so?
It really dislikes changes in current. So when the current tries to change, like it does in AC, the inductor pushes back.
This pushback is what we call.
Inductive reactance. And because of this resistance, the current in an inductor, it lags behind the voltage.
Lagging behind.
Like the voltage is trying to lead, but the current is dragging its feet.
Uh-huh. I see.
And get this, over a complete cycle, the inductor actually doesn't consume any power.
No power.
No, it just borrows energy and returns it. Doesn't actually use any.
Wow. Okay, that's unique.
Right. So now on to capacitors.
Okay, so if inductors are stubborn, what are capacitors like?
Think of a capacitor as a tiny reservoir storing electrical charge.
Like a little energy bank.
Perfect analogy. And in an AC circuit, the capacitor's resistance to changes in voltage is what we call capacitive reactance.
Okay, capacitive reactance.
And here's the cool part. With capacitors, the current leads the voltage. It's the opposite of inductors.
So it's like the current is impatient and the voltage is lagging behind.
Haha, exactly.
Amazing. So inductors cause the current to lag and capacitors make it lead.
Hmm.
What happens when we mix all three? Resistors, inductors, capacitors, all in a series circuit.
That, my friend, is when we get what's called an LCR circuit. And that's where things get even more, well, electrifying. Back for more AC adventures.
Absolutely.
Yeah.
We've covered resistors, inductors, and capacitors individually, but I'm really curious to see what happens when we put them all together in a series circuit.
That's where things get really interesting. And to understand these LCR circuits, we need to introduce a new concept. It's called impedance.
Impedance, okay.
It's denoted by the letter Z. And basically, it represents the total opposition to current flow in the circuit.
So like overall resistance.
Yeah, you can think of it like that, but it's not just a simple addition of the individual resistances.
Right, because we have to consider those phase differences created by the inductor and capacitor.
Exactly. The formula for impedance takes all of that into account. It's Z equals the square root of R squared plus the quantity XL minus XC squared.
Whoa, okay. That's a bit more complex than just adding resistances.
It is, but it gives us a complete picture of how much the circuit is opposing that AC current flow.
Okay, so XL and XC represent the inductive reactance and capacitive reactance, right?
You got it. And we subtract XC from XL because of those pesky phase differences.
Got it. Now, the chapter also mentions this really cool phenomena, resonance. What exactly is resonance in an LCR circuit?
Resonance is where things get really, really interesting. Remember how inductors cause the current to lag and capacitors make it lead?
Yeah, it's like they're playing tug of war.
Exactly. Well, imagine if those two effects perfectly canceled each other out. That's essentially what happens at resonance.
Wait, so the lagging and leading cancel each other out completely?
Pretty much. When the frequency of the AC source matches the natural frequency of the LCR circuit, something special happens. The inductive reactance and capacitive reactance become equal.
Oh, I see. And because they're equal.
They cancel each other out in the impedance formula. That means the impedance becomes minimum, just the resistance, R, and the current flowing through the circuit reaches its maximum. It's like the circuit is vibrating at its favorite frequency.
Wow, that's amazing. Circuit becomes super efficient at that specific frequency. And this is how radios work, right?
Exactly. Tuning your radio is essentially adjusting the capacitance of the tuning circuit. By changing the capacitance, you change the resonant frequency of the circuit. When that resonant frequency matches the frequency of your favorite station, bam, you pick up that signal loud and clear.
That's so cool. It's like the radio is selectively choosing which frequencies to listen to, all thanks to resonance.
It is. It's a beautiful example of how understanding physics can lead to awesome technology.
Okay, this is blowing my mind. We've got RMS values, phasors, LCR circuits, resonance. This is quite a journey. But there's more, right? What about this power factor?
Yes, power factor. It's all about how efficiently power is being used in a circuit. Ideally, all the power we supply would be used for actual work.
Right, but that doesn't always happen, does it?
Not always, especially when those inductors and capacitors cause phase differences.
Right, those pesky phase differences.
Yeah.
So is power factor a measure of how much of the power supplied is actually being used effectively?
Exactly, and a higher power factor means greater efficiency.
Okay, that makes sense. So the closer the power factor is to 1, the better.
You got it. In a purely resistive circuit where there are no phase differences, the power factor is 1. All the power is used effectively.
But most circuits aren't purely resistive, are they?
Nope. We've got those inductors and capacitors causing mischief. And when the current and voltage are out of sync, because of those phase differences, the power factor drops below 1. Some power is wasted.
Okay, so the wasted power doesn't just disappear.
Right, it's often dissipated as heat. That's why some electrical appliances get warm when you use them.
Ah, I see. So why does power factor matter in the real world?
Well, power companies try to maintain a high power factor in their distribution systems to minimize power loss during transmission. Think about sending power across long distances. If the power factor is low, a lot of that power is lost as heat because the current and voltage are out of sync.
That makes perfect sense. So how do power companies keep that power factor close to 1?
They use capacitors.
Capacitors again. They really are the superheroes.
They are. By adding the right capacitance to a circuit, you can compensate for the lagging current caused by inductive loads, like motors.
So they bring the current back into phase with the voltage.
Exactly, boosting that power factor closer to 1.
Amazing. They're like efficiency guardians. It's fascinating to think about how these tiny components play such a big role in power transmission.
They do. And speaking of power transmission, are you ready to dive into the world of transformers? They're the real game changers when it comes to getting power from power plants to our homes.
Oh, absolutely. Transformers have always fascinated me. They seem so simple, but they're crucial for our entire electrical grid. All right, let's recap this wild ride through the world of AC. We started by looking at how AC is different from DC, always changing direction.
And then there were those RMS values, giving us a way to measure and calculate AC voltage and current.
Those RMS values help us understand why AC shocks can be more dangerous too. Then we got into phasors, those spinning arrows.
Yeah, phasors. They helped us visualize those tricky phase differences that inductors and capacitors cause.
Right. Inductors hate changes in current. Capacitors hate changes in voltage.
Both storing energy, releasing it back, never actually using it up themselves.
Like a game of energy catch. Then we threw them all together. Resistors, inductors, capacitors, the LCR series circuit.
And we learned about impedance, that total opposition to current flow, and then resonance.
When the circuit vibes at its favorite frequency, Current just flows so easily.
like a superhighway for electrons. And that's how radios tune in to specific stations.
Amazing. We also talked about power factor, how much power is actually being used effectively.
And how our capacitor friends can save the day, boosting that power factor to avoid wasting energy.
Those capacitors are like the unsung heroes of efficiency.
Absolutely. And speaking of unsung heroes, we dove into transformers, using mutual induction to step up or step down those AC voltages.
Which is how we get power from the power plants to our homes.
Exactly. It's incredible how all these concepts come together to explain the technology that powers our world.
It really is. From the lights in our homes to the radios we listen to, AC is everywhere.
It's a fascinating world waiting to be explored. Who knows, maybe this deep dive has sparked a curiosity in you to learn even more.
Absolutely. There's always more to discover. Well, on that note, we've reached the end of our electrifying journey.
Until next time, keep those brain waves buzzing.
And remember, the world of science is full of wonders.